In this section, we're going to talk about exponential growth. So far, we've studied growth that occurs at a constant rate with linear functions and growth that occurs with projectile-type motion or quadratic growth. Now we turn our attention to relative growth. On the day Jeffrey was born, his aunt put $1 in a shoebox for him. Each year on his birthday, she decides she wants to put away double the amount from the previous year. So she puts $2 on his first birthday, $4 on his second. On his third, she puts $8, and so forth. If she continues this trend, how much money will she have placed in Jeffrey's shoebox on his 18th birthday? Okay. Doesn't sound like it, but this could get expensive. Okay, so first she started with $1 in the shoebox. Then when he was a year old, she put in $2. When he was 2 years old, she put in $4. 3, she put in $8. At 4 years, she put in double that, so $16. On his 5th birthday, double that, $32. And on the 6th birthday, double that, $64. How much is in there total? Well, we would add. So after he's just born, there's still just $1 in there. But after the first year, we would add 2 to the amount and we have a total of $3. Then we'd take that $3 and add the 4 added in. There'd be a total of 7. Take the $7, add 8. And there'd be 15. Then add another $16 the next year, there'll be $31. The next year we add $32, there's a total of $63. And the next year we add $63 to $64. There's a total of $127 in that shoebox when he's only 6. So this doesn't ask how much is in his shoebox on his total on his 18th birthday, but how much will she put in? So we're just looking at this first column here. But we need to talk about this first column and see if we can identify a pattern. Yes, each year we're doubling or multiplying by 2. But is there a more specific pattern going on here that we could write an exponential function with? Like something to the x power. Well, if you'll notice, I'm going to start with the 4. 4 is 2 squared, right? 8 is 2 cubed. 16 is 2 to the 4th. 32 is 2 to the 5th, and 64 is 2 to the 6th. And then if we go back, 2 is just 2 to the 1st power. 1 is 2 to the 0th power. Anything to the 0th power is 1. So if you look at this pattern, continuing on here, and we say n, well, that would be 2 to the n for n years. So our function could be f of x equals 2 to the x. So if we want to find out how much money is in the or how much money she'll put in on his 18th birthday, then we'll just plug into that formula. F of 18. 2 to the 18th power. That is $262,144. That aunt better be pretty rich by the time her nephew turns 18. And you can see this is how much he's, a graph of it, okay? At 6 years, there's 60 She puts in $64. An exponential function is a function in the form f of x equals b to the x, where b is greater than 0 and x is any real number. A certain bacteria reproduces in such a way that every minute the number of bacteria doubles. So at 8 a.m. or time t0, suppose we place a single bacterium in a jar. At 8:01, there's 2 bacteria. At 8:02, there's 4. At 8:03, there's 8. Same process as the previous example. Assume the bacteria continue to reproduce in this manner, with no loss in the number of bacteria. None of them die. And the jar is full of bacteria at 8:30. At what time will the jar be half full? Okay. Well, what do you want to say? You want to say if it's full at 8:30, it's going to be half full at 8:15, right? But that's not the case. The amount doubles every minute. So if it's full at 8:30, half of it was doubled from 8:29, right? So it was half full at 8:29. Using what you already know, can you develop a formula to model this data? And, I mean, it's going to be the same we just used, because we started with 1, 2, 4, 8, 16, 32. That's 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, 2 to the 4, 2 to the 5. So a formula would be, again, 2 to the x. And here's the bacterial growth. The general form of an exponential function is f of x equals a times b to the x. So there could be a number in front that's being multiplied after you've raised your exponent to the x power. Where b is the base, it's a positive number, not equal to 1. And a is the initial value, and x is any real number. Example 3 says, the sales data for a certain company for 8 years can be modeled by the data in Table 3. A plot of the data with an exponential model fitted to this shows that the function that represents the sales of the company is f of x equals 40.2358 times 1.88346 to the x, where x represents the number of years. And here's a graph of it. So each of those points were graphed, and this was the best fit. Well, where was our question? Guess I forgot to put it on there. What are the projected sales in year 15? So we've got through year 8 here. We want year 15. So all we need to do is plug in 15 for x. Now realize when you plug in 15 here, you cannot say that times that. It will not work. Give you the wrong thing. Order of operations says you have to do the exponents first. So you have to raise the 1.88346 to the 15th power and then multiply by 40.2358. And so the sales in the 15th year would be projected to be $535,745.66. Last example. A certain town had a population of 2,000 in the year 2001. If the population is increasing at a rate of 2% per year, what will the population be in 2021? So we're going to use a formula that looks like this. Okay? This is for increasing or decreasing a rate. Decreasing, this plus would be a minus, by the way. So we're starting with A, which is the initial amount, 2,000. And we're saying, 1 plus our rate. And the rate is 2%. We need to change that to a decimal. So 0.02 to the x. So our function would be 2,000 times 1.02 to the x. And it asks, well, what would the population be in the year 2021? We need to decide what x would be. It'd be the year 2021, subtract the year 2001. So that's 20 years from the year 2001. So we'll just plug in 20 for x. Again, make sure you put in your calculator first, 1.02 to the 20th power, and then multiply by 2,000. 2,972 people after 20 years. Look at Desmos with exponential growth. I'm going to take a look at example 3. The sales data for a certain company where we were given the function y equals 40.2358 times 1.88346 to the x. So here's our graph, and looking at it, you're like, well, wait a minute, it's negative, and sales aren't going to be negative. But it said that 1 was 55, so we're looking at it really small there. If we go up, you can see where 1 would be about 55 there, and it crosses the y-axis somewhere along in here at 40.2358, in fact. But let's change our window so we can get a better picture of this. So I'm just going to start at 0 because sales will just be positive. The year will just be positive. And let's go out 20 years, say. And then the y-axis, the sales will be positive, so I'm going to start at 0, and I can move it around as I need to. And we got a really big number earlier. Let's put in 1 million. Okay. So here we go, and I am going to go out just a little bit so we can see it better. But if, that's too big. Let's do this. Let's start with 5,000, just so we can look at it. Okay. I think I put in something wrong, but that's okay. So it said that 1, so where 1 is, was 55. So kind of hard to find that exactly. Two was 162. Well, those were the points that they're not necessarily the point of the graph itself. They were the points that this graph was fitted to. That's right. So the points won't match exactly what's in our table. But we were asked to find to the 15th power. So we can come over here at 15. We're going to have to scroll out some more. And let's see. There's 15. And that was the number we found, 535,745.66. Okay? So again, you can use Desmos to help you out with these. If we look at example 3, we had y equals 2,000 times 1.02 to the x. And let's see if we can find it. There it is. And we wanted to know after 20 years. So we in a bunch there. But there's 20 with 2,972 people, just like we found. Okay?